Sir, what is tetrahedron? About what you were saying this?
Yes, this is a diagram. You see, basically this is made up of four triangular plane actually. The base is a triangle, and you imagine that it's like a from the three vertex of the triangle, you just try to draw strings or take rods, for example, and keep it in this fashion, three rods from the vertex of a triangle. The structure which becomes is a tetrahedron. It is a structure of methane actually. CH4 has a tetrahedral structure. Okay. Carbon sits at the center, and the four hydrogen atoms, they are at the vertices of this tetrahedron actually.
Yes, sir.
Yeah. Anyway, we consider this case a regular tetrahedron whose side length is A for all the edges have the same side length. A.
Sir,
Hmm.
so what have you taught till now?
Nothing. I was just starting. I was saying there's a regular tetrahedron. Tetrahedron is basically a figure made by four planes. Each of the faces is a triangle, an equilateral triangle. The base is an equilateral triangle. The three side faces are also equilateral triangle. It's a tetrahedron actually. So in this case, what we have is the point masses, identical point masses, small m, placed at the vertices of this regular tetrahedron. The side length is A. Okay. For each of the edges is A. We need to find out the gravitational force exerted by each of these 3 point masses at the vertices, the base triangle on this apex over there. What is the net gravitational force which the 3 point masses placed at the vertex of the base triangle exert on the mass at the vertex actually? That's the question.
Sir, can you please repeat the question?
I'll write it down. The gravitational force, the net gravitational force or experienced by the apex implies the upper vertex. Okay. To figure out the net, we have basically a regular tetrahedron. Regular the spelling might be a bit incorrect for tetrahedron. We determine the net gravitational force acting at the point mass m kept at the apex. How much force will experience? Express your answer in terms of capital G. No, it's a regular figure. Angle you have to figure out, Shubham. This is a regular. The base is an equilateral triangle. This one is equilateral triangle. That is equilateral triangle. All the four triangles are equilateral. The base one and the three side triangles. They're all equilateral. Okay. You have to express the answer in terms of, let's say we just call F naught as gm square upon a square. So express the answer in terms of F naught. Okay. F naught is basically gm square. Dimension, it is the force. So we have to express in the units of F naught. How much F naught the force is there acting on the apex point mass because of the 3 point masses at the vertex at the base triangle. Okay, the vertex of base triangle.
So what has been done till now? So just join
That
now.
is just the first question I'm asking. Last time we talked about the gravitation, so I was asking a particular sum from there. There's a regular tetrahedral, tetrahedron, tetrahedral structure, and at the vertices, point mass small m has been kept. We have to figure out the force acting on any one of them due to the other three. In my diagram, I've asked about the apex over there, but actually there's nothing special about that apex point mass because it's a regular figure, so it will be same in all direction actually. So it will be the same for every point mass at each of the corner actually. The force with the other three, that will be same. ये वेक्टर नहीं होगा mod. Taken the quantity gm square by a square as f naught, so to express the force in terms of f naught. Gravitational force, well, it's a force, so obviously the vector
Yeah,
addition will
2
be
F naught.
what? 2. No, that is not correct. These three vectors are in 3 dimension, bit of imagination is required, but they're symmetrical actually. If you drop a perpendicular from the apex onto the base triangle, that will be passing right to the centroid, and the three vectors will be symmetrically located with respect to that perpendicular. 2 root 3 if not. No, that is not correct.
Sir, root 6
Sir, 1 plus.
What someone was saying. Can you repeat, both of you?
Sir, root 6.
I know that is not correct. And Ryan, you said root 6.
Sir, 1 plus root 3 F naught.
No. The correct answer will be root 6 if not actually. See the gravitational pull due to the 3-point masses at the base will be quite obviously in this direction. This will be attracting this point mass along this edge. This will be attracting on this edge. This will be attracting on that edge. Each of these force E is going to be F naught. That much is quite sure. Each of these force in magnitude, which is nothing but F naught, the same gm square by. These are three F naught which are acting, but the point is they're in three dimension that at different angles actually. Difficult to imagine, but I mean you'll have to consider three vectors which are well. If you just consider those three vectors, they will be actually a way that
Sir,
yes.
sir, can we do like this? If, we can concentrate the three masses at the base at one point
No, you
and then
cannot do that.
calculate.
Cannot do that. Root 10 is wrong, Shubham. You cannot concentrate in your three masses at the center. That is not allowed. Okay, that can only be done in a few specific cases. Specifically, when you're dealing with spherical objects, spherical bodies. When you're outside it, they can be concentrated at the center. But you must, but the spheres must be uniform, homogeneous actually. Or at least the density must be spherically symmetric. Only then you could do that. Otherwise, you can't. For example, if you take two cubes, for example, you can't put the two cubes. I mean, think of them as center, point mass as center. That can't be done. Okay, it can't be done actually. What you could see in this case, however, is that if I imagine it looks like a circle. No, the three. The three forces that actually they look something like this. They are in three dimension around a circle, you might say. With respect to the center, you can consider a cone, for example. Think of a cone, conical surface, and the apex angle will be get calculated over there. Then the three forces lie along the surface of that cone actually, and are equally separated, equally spaced, which implies that the base circle, if you consider, the three tips will be 120 degrees apart actually. The angle between them is 120 degrees, 120 and 120 along that circle. Okay, a symmetrical situation actually. Now, if I just resolve the three forces into components, horizontal and vertical, then what I say is that the horizontal components will be actually equal by symmetry, and they will be located along the three directions which are at 120 degrees with respect to each other, like the three cube roots of unity actually. If you consider in this case the component in the horizontal direction of the three forces, all the three forces, the horizontal components.
That means the net force of the horizontal component is 0.
Exactly. The three horizontal components will cancel out because they're equal vectors located along the three directions of the cube roots of unity actually. Or you can say three vectors which are equal in magnitude and they have angle between them as 120 degrees. To draw them from the same point, the summation is going to be 0. Okay, that is why what survives is just a vertical component. So I need to just find out the vertical component of one of them and then multiply it with 3. That will be required as well. How do you figure out the vertical component? For that case, I need the angle between a force vector and the vertical, which will be passing through that point. Now, because symmetry, if I draw perpendicular from the center over there on the base triangle, that perpendicular will be actually coinciding with the center of the base triangle, isn't it? Because of the symmetrical situation that we have, if I drop a perpendicular onto the base plane, the base triangle, that perpendicular or the foot of the perpendicular will be actually lying right at the centroid, isn't it? Because of symmetry, it will be same for all the three actually. You can see that this length, and this length are equal by symmetry, and that is why it is centroid over there. It's actually center of the circumcircle over there. Circumcenter also you can say, but equilateral triangles have all of them are the same thing. So let's consider in this case, let's say this one is A, that is O, and this is B. Let us consider the right triangle AOB. Notice in this case that the angle between F0 and BO, if that is theta, then I require F0 cos theta actually. ठीक है. So I'm just looking at the right triangle. This is A, that is B, and that is O. This is 90 degrees. This angle is theta. F naught acts along this direction actually. B. I require therefore net force cos of theta. Okay. Now, how to find out cos theta? First, for that case, we notice that the base triangle is A, and this one is actually the line joining the vertex to the centroid. So that'll be 2/3 of L. If you look at this this base triangle is also equilateral triangle actually. If you look at that base triangle and equilateral triangle, this one is actually the line which we have, AO. If we look at the perpendicular drop, it will be also in this case the altitude. This angle is 60 degrees, the base triangle. So A sine 60 is what we get the total length, this full length from here to here. This altitude is A sine 60 degree, that is root 3 by 2A. So this being the centroid, it divides the entire thing in the ratio 1:2, which implies that length I'm looking for OA is 2/3 of A sine 60 degrees. I have in this case OA as 2/3 of A sine 60 degrees, which implies it is 2 by 3A into root 3 by 2, which gives us A by root 3. That length is A by root 3 actually. OA. And therefore, because that is A, this is known to be A by root 3, I can find out OB as well. OB will be in this case root over of A square minus A square by 3, which implies this is root over of 2 by 3A. This edge.
Sir,
Hmm?
sir, please repeat that OA part, the 2 by 3A sin 60 degree.
Well, OA is actually the line joining the center to the vertex A. So I was saying that if I extend AO to the other side, it is being an equilateral triangle, that will be also the, say the altitude actually. So the length will become A sine 60 degree, implies root 3 by 2A. And O being the centroid, it divides this median. It's also median actually. It divides this median in the ratio 1:2. So the required length AO becomes 2/3 of the entire altitude, which is A sine 60 degree. Okay.
Okay, sir. Yes, sir, understood.
Once I get to know OB, I can find cos theta. Cos theta becomes base by hypotenuse. Base is this one, hypotenuse is A, so cos theta turns out to be root 2 by 3. And therefore, if I look at the net force, so net force, if I consider, that turns out to be 3 times F naught cos theta. And that gives us in this case 3 into F naught into root over of 2 by 3. That makes it root over of 6 F naught actually. Okay, that is a force.
Sir, can you please explain that OA again? That 2 by 3A sine 60 degree.
Well, I said focus on the base triangle. The base triangle is an equilateral triangle. O is a centroid and A is the one vertex. So OA is a line which joins the centroid to a vertex. I was saying that if you extend AO to meet the opposite side of the base triangle, in that case, that is also acting like an altitude. It also is a median because it's an altitude and the hypotenuse is A, one side of the triangle, and the vertex angle is 60 degree. So I get A sine 60 equal to root 3 by 2A equal to the altitude. Now, because the altitude is also a median, and the centroid divides the median in the ratio 2:1, 2 closer to the vertex. That is why I have taken two-third of the entire altitude. Okay. That is
Okay.
what it's coming up to be two-third of a sine 60 degrees. Okay, is it fine? So last time I asked a question where I said that if you calculate the gravitational pull of the sun on a point mass on the Earth,
Explain this once again.
what? Cannot get. What I said is if we compare the net gravitational force with the sun. Oh, Shubham, why are we considering only the vertical? Because the horizontal components cancel out, you see. I said a bit earlier, the horizontal components will be actually three equal vectors which are mutually at 120 degrees with respect to each other. So their sum becomes 0. If I have three vectors at 120 degrees with respect to each other and equal, well, think of the roots of unity by the way. 1 omega omega square. They're also similar. The three vectors at 120 degrees with respect to each other. So sum is 0. You can also form an equilateral triangle from these three vectors actually. That is why sum becomes 0. Okay, what I was saying is I asked you last time, we evaluated or we numerically calculated the gravitational pull of the sun and the moon on a unit mass on the earth actually. And we obtained that the force exerted by the sun was in fact roughly 100 times more than that of the moon on the same object actually. So if we have on Earth some object, then it is being pulled by the sun, also by the moon, obviously also by the Earth. The Earth is pulling with the greatest force actually, but that is because Earth is closest. However, I said that the sun pulls on that object, the moon also pulls on that object. And if you compare the forces of the sun and the moon, the force of the sun was roughly 100 times more compared to that of the moon actually. Yet, I said, yet the tidal effect is always caused by the moon. Why is that so? The tidal effect is actually caused by the gravitational pull of the moon, basically that's what I say. Why is it happening that though the sun's force is more compared to the moon, yet the tidal effect is due to the moon? Twice a day. Yeah. Anyway, actually the result that is happening, it turns out that tidal forces are not proportional to 1 by distance square, but they behave or they vary as 1 by distance cube actually. Tidal forces they turn out to be varying as 1 by distance cubed, not square. And if you just look at the force, turns out if you just look at the force by calculating the cube of the distance in a denominator, the sun's force becomes much lesser compared to the moon. Actually, it just depends on the radius of the Earth and inversely on the cube of the distance actually. Anyway, doesn't matter. The point is that the tidal effects are slightly different. They're actually we may calculate them later on, not now. But they depend inversely on the cube of the distance actually, and that is why the sun's attraction becomes or sun's effect becomes too less compared to the moon actually. Okay. Exact calculation will have to wait a bit. Some time is required.
Sir, can you please repeat once? Why?
I said the tidal effect, the tidal forces, which are responsible for the tides, they actually are inversely proportional to the cube of the distance. Cube. So you'll have to calculate the cube of the distance between the Earth and the Sun, and cube of the distance between the Earth and the Moon. So in this
why?
case, why?
Sir?
I said for why you have to wait a bit. Okay.
Oh, okay, sir.
Yes.
Yes, I was going to ask the same thing, that why that the same force is acting on us and the sea as well. So why is would
No, no,
would
actually, it turns out that the force, that tidal effect is slightly different. Okay, they are not exactly just a gravitational pull. They also depend on the mass of the water bodies, actually. That I'll just do after we have been more familiar with gravitation a bit. Then I shall take that up. Okay. So, fine.
Yes, sir.
Okay. Normally, the gravitational force is universal, so it will be acting between two protons inside the nucleus, also between two galaxies, for example. So, on the bigger scale, gravitation is the one force which dominates the entire universal structure. Okay. If we talk about the terrestrial gravitation, gravitation of the Earth itself, for example, you might be knowing that we know that this is Newton's gravitation. Newton was entirely whole and soul responsible for this particular explanation of gravitation. There is one very interesting, say you can say a problem, in fact, which Newton was unable to explain, or at least the idea. If you take up the theory which was given by Newton, it is something called action at a distance principle, okay, which implies that we have 2 point masses, one and one over here, and there's a force between them. So if I change the position of this point mass from here to here, the force instantaneously changes. That's the idea, okay. That is what the principle of action at a distance means. If you just change the position of one of the masses, the force which it exerts on the other one, it will immediately change. Okay. However, there is a principle from the relativistic mechanics, or at least which is known to be correct. Actually, it's much more truer than the Newton's laws, and it is going to put a upper limit on the speed of any kind of information carrying signal. Actually, any kind of signal which can carry an information cannot travel with a speed greater than the speed of light in free space, which is around 3 lakhs kilometer per second. Okay. Now the idea is what? If I consider, for example, the sun, we know that sun is at the center of the solar system, and that is what keeping the planets in circular orbit, approximately circular orbits. The gravitational pull of the sun provides the required centripetal acceleration, and that is why the planets are revolving around the sun. Now, say for example that the sun abruptly vanishes. Suppose, for example, that somehow some magician just vanishes the sun immediately. Okay, and if you consider the light takes around 8.2 minutes to reach the earth from the sun, isn't it? So if the sun vanishes at some moment, that information will reach the earth only 8.2 minutes later, isn't it? So during the time interval when the sun is not there, the earth still continues to move in a circular path. At least that is what should happen actually. According to the Newton's gravitational law, the moment the sun vanishes, the force on the earth will be zero, and therefore there is nothing to provide a centripetal acceleration, and the earth should immediately leave the orbit and go along a tangential direction.
Sir,
Yes.
sir, please repeat the last point. I can't understand it.
Okay. What I was saying is
No,
what?
it's imaginary. Vanishing sun.
Sir?
Yes.
So it will continue on its the same original path for some time. It will not so it will not deviate even a bit. See, if the sun disappears for a slight amount of time.
Slight amount. The information reach only after 8.2 minutes, isn't it?
So till 8.2 minutes, the Earth will continue moving in the exact same way in which it was moving.
How can it happen? There's nobody to provide a centripetal acceleration.
Yes, sir. So it should go in a tangential path. It
Yes,
shouldn't.
the sun
That
vanishes.
There are some.
Newton's mechanics predict. You see, what I was saying is, This is the action at distance principle. The force on the Earth will change instantaneously the moment the sun vanishes. Say, for example, it vanishes. This hypothetical situation. The point is, what I meant to say in this case is that because the sun has gone, Newton's gravitational law suggests that the force on the Earth should become zero immediately because there is no sun. So m is zero, mass of sun, isn't it? However, it is the sun's gravitation which is providing centripetal acceleration, and because sun is no longer there, gravitational pull is gone. What should happen is the Earth should feel now no force, and therefore leave that circular orbit and go along a tangential path. Okay. However, the problem, or what in this case objection we have for this particular idea,
With what speed?
again,
So with what speed it should go in the tangential path?
with whatever speed is rotating in the orbit, revolving rather, which you can calculate. This
The
is
speed will be same now.
what?
I mean, after leaving the path, after going the tangential path, the speed will be same.
Yes, it will be same.
Yes.
Which you can calculate. It will be actually turning out root over of capital G into mass of the sun by distance between the Earth sun whole, whole, nothing whole, but just Earth sun distance. Okay, that is a different. That's a different. So the speed will not change actually. But the point what I'm asking in this case is, this principle, at least according to Newton's gravitation, the Earth should leave that path instantaneously, isn't it? However, the objection is coming from the later theory of the relativity principle, actually, Einstein's relativity principle, which is known to be correct, actually. By other experimentation, it has proved that this theory is valid. Theory is valid, and this theory puts an upper limit on the speed of any information carrying signal. Anything which can carry some information or mass, for example, it has an upper speed limit, and that is the speed of light in free space. Nothing or no information bearing signal can travel at a speed more than the speed of light in free space. That is around 3 lakhs kilometers per second. Light starting from the sun, traveling with that speed, reaches the Earth roughly around 8.2 minutes later. Okay, it takes around 8.2 minutes for light to reach the Earth from the sun. Now the sun has vanished. This is also an information, and this can only be carried by what?
Sir,
I was saying, Avibrata, that the moment the sun vanishes, according to Newton, the force between the Earth and the sun has become zero. So the Earth is no longer experiencing any gravitational force which was providing the Earth with a centripetal acceleration, and therefore it cannot continue along a circular path. It should leave the circular path, go along a tangent. Okay?
Yes, sir.
Instantaneously.
sir,
Wait a moment, Manak. On the other hand, I was saying that there is an upper limit on any information carrying signal, that is the speed of light in free space, which is around 3 lakhs kilometers per second. So the sun has vanished. This information can reach the Earth only when the light stops coming, and that will happen after 8.2 minutes actually. So till 8.2 minutes, we do not know. The Earth doesn't know actually. The sun is not there. So it should
Sir,
continue that circular path.
sir, but if when the force vanishes, the Earth also leaves in the tangential direction,
But
and
when the
as it
force
leaves,
vanishes, that is only apparent after 8.2 minutes. Before that, the Earth doesn't know, because that information is coming from the. It can't come at a speed greater than the speed of light. So it cannot appear. It cannot come to the Earth information.
Sir, but the time taken will be a bit longer than 8.2 minutes, sir, because it is a standard time of means light to from of the light from the sun to reach the Earth. So, but after it leaves in a tangential direction,
Yes.
it also has a speed. So
You don't get the question actually. I was saying that according to Newton, the Earth should leave that circular path, go along tangent. But according to a more correct form of a correct version of physical principles, the Newton's theory is a bit wrong in that case. Uh, According to Einstein's relativity principle, nothing can move at a speed more than the speed of light in free space. So the information that sun has vanished. It can only reach the earth after 8.2 minutes. So meanwhile at 8.2 minutes, there is no sun, but yet the earth is going to move in a circular path. It is apparently a contradictory thing. That's an apparent paradox actually. I was asking how can it happen?
Sir?
Yes, Hanak.
So the the force exerted, so it is actually an interaction between molecules.
What?
So and that so force, so it is actually an interaction between molecules. So and that interaction cannot happen at a speed faster than the speed of light.
Which molecule are you talking about? The molecule of the sun and
So,
the earth.
yes, so any force is at an interaction between molecules. So that interaction cannot happen faster than the speed of light.
So you mean to say what?
So that is the reason why uh, the Earth will continue to go in its path for 8.2 minutes.
But during that time, who provided centripetal acceleration?
So that interaction which that sun exerted, which means
Sun is not there. Sun is gone.
yes, so that interactive force, it took some time to reach the Earth, like at the speed of light.
So that force that the sun exerted previously.
So other planets,
Momentum, sir.
other planets are also there.
There is gravitation.
So it will it will continue to circle the in its momentum.
Yes, a
Really?
moment.
But to continue in a circle, it requires centripetal acceleration, isn't it?
The inertia also will be there.
Inertia. Inertia provides centripetal acceleration. That's what I meant to say.
No, sir. Yes,
Because of inertia, it should go along tangent. If you take a stone, tie in a thread, and then and whirl in a circle, your thread breaks, for example, it doesn't move in a circle. It goes straight along tangent. That is the inertia over there. It tries to continue on a straight path. It is because of force it is bending. So there is no force, it will not bend. Okay. Actually, the apparent paradox is going to be resolved due force of relativity. The relativity principle just puts a speed limit on the velocity. It doesn't talk about the forces actually. The gravitational force is dealt with in more general detail in the general relativity theory, which talks about gravitation as if it was a curvature of space-time.
sir.
Yes.
Sir, that the sun that the earth before vanishing, that will provide the centripetal.
Before vanishing, they have provided the required centripetal, so it just kind of gave something in advance. No, actually, you see,
Don't know.
no. The point is that this action at distance principle is not valid actually. The action at distance principle says we have 2 point masses, there is a force between them. This principle is slightly a bit wrong. In fact, we might say that there is actually an intermediary in between them, which is called a gravitational field. We say that this point mass will create a gravitational field, and when this other mass comes in that gravitational field, it interacts with that field. Then it can experience a force. The idea is that we have the action at a distance principle is an interaction between a particle and a particle. That's the action at a distance principle. It was a classical principle.
So that means both the particles should be in the same gravitational field.
Exactly. The new idea or the new principle is not the action at a distance, but we have a particle creating a field, which will be in this case a gravitational field, and this interacts with the other particle. You might think of the sun as if it was a spider sitting in a great web actually. Okay, so it has woven a web around itself, and these planets, they are actually stuck in that way, this web. In fact, the sun knows about them by means of tugging in that you say the web. If you just look at some spider sitting at the center of the web spreads everywhere. If some insect kind of gets stuck over there, in that case the spider knows because the oscillations which it caused in the web actually. Fine. In a similar fashion, in this case, you can imagine that the sun also sits in the center of a giant web, which is invisible to us, but the plants can feel it. That web is like the space time around us. Fine. So when the sun vanishes, it creates a ripple in that web actually. When it's almost like you take up a rubber sheet, pull it down and leave it. There's a ripple effect coming up. It's happened something similar. The sun, when it vanishes, it creates a ripple in that web. And that ripple spread out, okay, like a gravitational wave, in fact. Y implies any structure, anything that you have, it has a tendency to support a wave structure actually. Where when you disturb something, leave it with some elasticity, it creates a mechanical wave. Fine. Take up a scale, for example, or just talk up when I'm speaking, for instance, I'm basically doing a complicated business, but I do not, nobody kind of experience or I would say pay any much attention to that. It happens naturally. A lot of things are happening when I speak, for example. Ultimately, the air around my mouth that gets pushed and pulled, there's a wave traveling by. Okay, that wave is a feature which is always going to happen whenever you have an elastic medium. That's an example of mechanical wave. Gravitational and electromagnetic wave do not require that medium, in fact. But nevertheless, it is happening that when the sun vanishes, it leaves a ripple kind of thing in that space time over there. Yeah, the speed limit is the same. The speed of light, 3 in 10 per 8 meter per second. So what happens when the sun vanishes? That yes, Ryan, wait a moment. When the sun vanishes, this creates a disturbance, a ripple in that web kind of thing, and that ripple spreads. And that wave actually does carry the information that the sun has vanished. It reaches, and in fact, it also exerts a force. I said the force is not due to the field, not to the particle. So the field is still present. It is almost like an impulse, which I said it takes some time to for the web to finish. Actually, you see that if you drop a pebble in a pond, the ripples spread. So it takes some time for the ripple to spread. Actually, isn't it? It has a finite limit. The same thing. When the web that we have over there disturbed, that ripple is still expanding, and that does so with the speed of light, and that wave is still present. The gravitational wave is the consequence. However, the field is still there. The field is gradually diminishing. Okay, this field has an independent existence, pretty much like the light. Light is also an electromagnetic wave, actually. ठीक है ना? So it takes a bit deeper actually into the question exactly what gravitation is. This is a modern theory, yes. This is at least modern than Newton actually.
So what will create the wave?
What?
So what will create the wave?
The vanishing of sun? You see, when the sun is there, it is almost like it has stretched the web around it, okay? There's a stretching of the space-time fabric around the sun. When the sun vanishes, there's a kind of oscillation happening in that fabric. You have seen a trampoline? Have you ever played trampoline?
Sir, can you please explain this again, sir? Everything is going above my head.
Sir,
Hmm.
sir,
Yes.
so that means the sir after after it is there is no sun. So then, sir,
There
at
is a
that
field.
instant or for the very few 8.2 minutes, sir, the gravitational field is giving the centripetal acceleration.
Exactly. Because the field is still
Yes,
present.
yes, sir.
Okay. Uh, or could I mean, say somebody asked what
Sir?
okay. Well, yeah, I was saying, have you seen a trampoline? If you just put a heavy ball in the trampoline, say steel ball, you put in the trampoline, if you just make a dent around it, isn't it? The trampoline is going to go down like this. It is going to be stretched. Trampoline is elasticy actually. Once you remove this ball, the ball is suddenly gone. The entire stretching part will kind of rebound and is going to settle down after some oscillations, isn't it? It's a very similar principle actually. Only thing, this is not happening in a trampoline. It's happening on an invisible trampoline, which is a space-time around us. But the effect is still there. Orkodev, we just don't think much of it. What the entire story meant was that the field is the one which is present, even the particle is gone. That field is like an invisible web around it. Okay, it's like you can see, imagine the sun is like a great octopus over there. It has tentacles flying all around over there, and it can touch all the planets and well hold them and pull them, kind of. Newton's before Newton, people used to believe that invisible angels are pushing the Earth around the sun. Okay.
Sir,
Sir,
Yes. Ryan, what are you saying?
sir, how will you know that the wave will provide the centripetal acceleration for 8.2 minutes only? That can be
That is
more.
the rate at which expanding, actually expanding the speed of light itself. So by 8.2 minutes, it just go out of the radius of the Earth. Actually, it's almost like you see, it's kind of going. It's like a shock wave. It's like a ripple which is expanding. Fine.
That the speed of the wave and the speed of light at vacuum will be same.
Exactly. Same. Gravitational wave also does the
Sir,
same. In fact.
sir,
Yes.
when the information is reaching to Earth, sir, at that moment only the gravitational field will be completely gone.
Through the it will be gone above beyond the Earth. Actually, after that, Earth will not feel the gravity.
Yes, sir.
Okay. It takes some more time to reach Jupiter.
So that
sir,
means, sir, they are simultaneous.
Yeah. Yes.
sir.
Painak, you're saying something?
Sir, can you
Yes, sir.
please explain the repelling effect again, sir, please?
Haven't you seen? Haven't you ever dropped a pebble in a pond, still water has become too slow? There are ripples created.
Yes, sir.
Exactly, Shivam. That is what the picture is. It is like a space-time fabric that you have sent. So imagine the sun also dents it a bit more. It's like a top membrane.
Sir.
Uh-huh.
So then it means that the sun is affecting the space around it.
Definitely.
Sir,
Space-time
but
boats.
sir, but on what? So the
On
space
what?
is empty. So
No, no,
it is exciting a space on what's a dark matter.
no. It's affecting the space-time around itself. Things is a bit complicated actually. You can't think of space separately. In Newton's mechanics, we think of space separate from time. But the correct version, which is for the relativity, is in fact
It's
thinking
a
of them
space
as
and time and the yes sir,
parts.
same space time. Yes sir.
The sun is in that space time and it does affect it. Okay, everything affects you. Also affected me. I'm also affecting it. But our effects are too minute actually. Forget about what is dark matter. Dark matter is what we can't see. That's it. Why is something dark? We can't see that. That's it. Anyway,
The too
forget about that.
okay.
What?
The too much complicated.
Too much complicated. Well, yeah, I mean, so the mathematical detail is definitely complicated. But think of like a story. Yes,
Sir, is it just a hypothesis?
no, it's a theory. And
Sir, but how could the scientist provide means this
obviously,
theory?
you think any theory dealing with astronomical scales or astronomy, for example, it cannot have direct proofs over there. Okay. Normally, what happens is a consequence of that theory is measured. Fine. If that is found to be correct, then things are correct. That is how it works. Okay.
So that means
Okay, sir.
all are not hypothetical one. This practically present.
Definitely. What is hypothetical you're asking? The gravitational wave? It is very real. Recently, people have observed it in a bit more detail actually because of some black hole uh, pulling up some other star. There was a large ripple in the space-time fabric which was measured actually.
Sir?
Yes,
Sir, if gravity can affect space-time, it means that if any object in any part of the universe disappears, it is affecting all other objects in the universe
definitely.
in some way.
Exactly. And for your kind information, gravity is the curvature of space-time actually. Okay.
Means
So what does that mean?
Yeah. What does it mean? Well, I mean, an analogy can be given, but exact thing will be obviously a bit
So
more hard.
curvature on the basis of what? Curvature.
What is the basis of?
So no, curvature. It means, sir,
Listen,
there is a
wait. Listen to a story. Say, for example, you think of a globe, okay, a spherical object, a globe. Uh, a sphere is actually present in three dimensions. That's a two-dimensional surface. But strictly speaking, it is present in three dimensions, isn't it? Imagine, for example, I think I have told a story earlier. Say we have some flat beings which are living on this globe. Flat beings which are living. Living implies Living, not Leaving. So we have flat worms living on this globe. So they do not have any idea about the height, about the height from surface. They have no idea because they can't go beyond it, and they're entirely flat. So they are stuck to the surface. Their whole life is on the surface actually. There's no way that they can measure they can see the curvature in the usual sense. They cannot see the curvature because they are right inside it. Okay, they can only see the curvature of the globe if they go up, but they can't do that. Okay. However, they can measure this curvature if they are more mathematically oriented. For example, they can draw triangles, big triangles. You can see that on the surface of the earth, for example, the globe, if you take up a globe, start from North Pole, go along one of the meridian, turn on the equator, you have about 90 degrees. Anna, go along the equator for some distance, again turn along one of the meridians, again 90 degrees. So already have 180 degrees. Third
more
angle
than
is
90 degrees.
positive. So you already have more than 180 degrees in that triangle, isn't it? So this kind of situation can be, those flatworms, they can know about the curvature of their world by actually not relying on the direct observation, but the indirect one. So mathematical things can be seen. Okay, that is what kind of situation we are in as well. We are also like a flatworm. The difference is that we are stuck in three dimension. Say we can't see the fourth dimension basically because we're inside. If I want to see the curvature of this space I'm talking about, we'll have to go beyond this four dimension. We have to go to fifth dimension. We can't do. We are stuck right now. We cannot transcend a dimension. That is why things have to be measured. Some other indirect consequences should be measured. Okay, and that
the
was
fourth
measured.
and fourth dimension, fifth dimension practically present.
Practically implies what you're living inside is space is three dimension. The time is four dimension.
Which one fourth?
Sir,
Space, length, breadth, height,
No,
and
sir, which dimensional?
four dimensions time.
But we can see time.
What?
Time.
Yes, time. Time is a four
Yes,
dimension.
so
The time is dimension. Like that. Three
Yes,
dimension.
it is a dimension. Time
sir, the how are the cubes aligned in the fourth dimension?
in the four dimension how the cubes aligned.
It's
Sir,
becoming more complicated.
lines make up the two dimension, and those areas make up the three dimension, and those cube like things or cuboid like things make up the third dimension. And therefore, to make the fourth dimension, those cubes need to be stacked together. So how?
That is does not making in the four dimension you can see the cube moving with time actually. Then we have a four.
And sir, five dimension is
Relative surrounding.
It will be something which is beyond by us. We can't imagine because nobody has seen it. Isn't it? Well, people now believe we are living in 13 dimension. You know that?
13.
Yes. Four dimension is known, but the rest of dimensions are curled up. They are very, very small actually. That's what they say. I don't know how to imagine. If I just wave my hand, I'm passing through 13 dimensions. You know that? I mean, say this is just a theory, but actually there's a difference exactly how we think of dimensions and how these mathematical things are there. Yeah, string theory is more kind of advanced, but still doesn't deal with dimensions actually. Anyway, forget about those things. For the moment, we can think of like stories, okay? But one thing which is true.
Dimension.
What?
What is the fifth dimension?
Name it whatever you want. Just a fifth dimension. What else?
Okay, sir.
You can't see that because we are stuck inside. We are like those flatworms. Okay?
Yes, sir.
Do not think of this much. I mean, say these are just kind of good thing right now as stories actually, though they have some basis. But right now it's difficult to imagine them because we don't have any intuition about them because we don't have any experience about them. Fifth dimension is Corona. Yes, Shubham, that is what you can say. It's a new dimension added to our lifestyle, the Corona. Yeah. Anyway, what was important from all these things is this particular fact: the particles creating a field. Okay, all objects they create a, for example, Earth also creates a gravitational field around itself. It is difficult to imagine, right? Because we have no experience at all. But where our imagination is not very much of help, we have mathematics coming to our help. And 8D audio, that is 8D audio is simply a marketing term actually. Okay, it is nothing to do with the mathematical dimension. It is just a marketing terms. Okay, you go to those cinema hall where they give you some 9 dimensional, pata nahi how many dimension experience. You just go along in 3 dimensional goggle. You just see, then your chair will sway, and then when there's water coming up, they'll spray some water in the head, so you'll feel the experience as well. If you're passing through a garden, they'll just spray some perfume as well, so you can. That is what. That's a different thing. It's a marketing term actually. Anyway, coming back to the gravitation part. What actually I meant to say that as far as Newton's gravitation is concerned, it talks about this kind of model, but this is slightly mistaken actually. Okay, we cannot have particle-particle interaction only because that will be in violation with the more truer laws actually. Okay. Anyway, still we have talked about Newton's law because it's enough for us. In fact, we live in Newtonian world around us. There's hardly anything working on relativity principles. Let's talk about the what actually talking about is the gravitation of a spherical body, like the Earth, for example. You see, what actually I was saying is Newton, when he gave this theory of gravitation, there was a problem dealing with the gravitational pull because of spherical bodies. Okay, so he kind of invented the entire integral calculus to prove that the gravitational force of the Earth can be obtained by thinking of the Earth as a point mass right at the center. Okay, this is called a shell theorem. Actually, there's something called a shell theorem in gravitation. I'll just talk about the result. Shell theorem, what it says is that if you have a, let's talk about first a spherical shell. It is a hollow sphere, like a football, for example. If you have a spherical shell which is homogeneous, uniform, if you have a uniform or homogeneous spherical shell, so a spherical shell, which implies that it is empty from inside. The radius is say capital R, and the mass is capital M. It must be uniform, homogeneous actually. Fine. What the shell theorem says is that if you take up another point mass, or if we just talk about the gravitational field, turns out the gravitational field is nothing but a force point of mass actually. Like if I on the Earth, if we talk about the gravitational acceleration due to gravity, that is same thing as the gravitational field actually. Okay. Anyway, you can just talk about the force itself. If I take up a point mass within the shell will not exert any force on it actually. So if I just consider this shell theorem, it says that the gravitational force exerted by the spherical shell on a point mass kept a distance r from the center is simply g m by r square if r is greater than capital R and is equal to 0 if r is less than capital R. Which implies if we talk about the gravitational force which the spherical shell exerts on another point mass, if the point mass is placed inside the spherical shell, the shell will not exert any gravitational force. Okay. The point mass small m will not experience any gravitational force due to the spherical shell if it is inside. But if it is outside, the shell, then as far as the force is concerned, small m, you can see the force is elected as if the entire shell was a point mass at the center. So as far as small m is concerned, it sees the spherical shell as if it was a point mass right at the center of there. Okay? So for spherical objects, spherical shell rather, from outside the shell, as far as the gravitational force is concerned, it seems as if it was just a point mass at the center of the shell. Okay. From the
Sir,
inside point, there is no force at all. Yes.
sir, we can consider as hollow sphere.
Right now, the spherical shell is a hollow sphere. Yes. Okay. We should use this idea to obtain the gravitational force, which
Sir,
the
sir, when
yes,
the particle is on the surface,
that's undefined. Many people take it as an average, but technically speaking, this is a mathematical problem actually. Because mathematically we have just a surface, but in real sense will be always certain amount of width to it, isn't it? So many people just say that take the average right at the surface, but there's no idea of how can you just have a point mass at the. This is a two-dimensional surface actually. There is no thickness about it, either inside it or outside it, isn't it?
oh, sir, that means if it is in the surface, that means it is definitely greater than the capital R.
You can say that.
Yes, sir, because that is greater than the average.
Yes, because if it is on the surface outside, okay.
Okay, sir.
Sir, then smaller should be capital R in the place of GMM by capital R square. The force should be.
Yeah, you could take it if you wish. I have intentionally left it unequal because right at r equal to capital R, it is a bit undefined over there. Okay. Yeah, okay.
Hmm.
Hello? हाँ सर बोलो मैं बढ़िया तुम बताओ अच्छा मुझे हो गया चलिए ऐसा आप घर से ही कर लो ना चलिए ये कर सकते हो इससे अच्छा चलो कोई बात नहीं आपके पास कोई करनी अच्छा कोई बात नहीं थोड़ी काम हाँ हाँ संडे को नेक्स्ट संडे हो सकता है लाइक पर बंदा जो एग्जाम में मुझे लेके जाना पड़ेगा ठीक है सेकंड हाफ में होंगे हाँ जरूर कोई बात नहीं क्लास के बाद में कोई बात नहीं एक्चुअली पता नहीं उनको ध्यान नहीं है घर में बात करते Anyway, is this result clear enough? Somebody was asking something? Okay. Now, if I consider in this case a solid sphere, like for example, the Earth is more like a solid sphere over there. So look at the solid sphere, what happens? Acha, I was saying that is equal to sign. I have left this intentionally not present over there because strictly speaking, at R equal to capital is a bit undefined. Okay, you can be either outside or inside, but not on this. That. Okay, but many people will take the average of it, but for us it will be not important. We can just leave it for the moment. Okay, we can just say it's undefined by this surface. Okay. If we take on the other hand a sphere, like a solid sphere, if I take up a solid sphere, what happens then? Now it's no longer a spherical shell, but a solid sphere. So the mass capital M is distributed throughout the sphere, uniform, homogeneous sphere, the radius is capital R. Now, when I'm outside this, this point mass is outside this sphere, we can still consider the entire sphere as a point mass in the center. The reason is that I can think that the sphere is actually made up of a large number of spherical shells like these. Lots of the spherical shells are put concentrically to make this solid sphere. And think of it this way. Okay.
And all the cells are
what?
concentrated to the center.
Yes, each of the shells will be taken as a point mass in center. So in effect, the entire sphere will be taken as a point mass at the center. Okay. On the other hand, what if the point mass is somewhere inside? Inside implies maybe you can just bore a thin kind of boring and put the point at the bottom over there. That thin boring will hardly affect the mass distribution, and that point mass will also then coming inside, isn't it? So what happens if I consider this point mass M inside the surface, inside the sphere? Say for example, now the point mass is over here at a distance which is equal to small r from the center. In this case, how much force will this point mass experience? How to find this one? See, in this case that we can see that this point mass is actually present inside some of the shells and outside some of the other shells, isn't it? Those shells whose radius is more than small r, they're actually outside, or rather the point mass is inside those shells actually. Whosever radius is greater than small r, like these shells over there, this point mass is sitting inside them, and therefore these shells don't exert any force on them. The part of the sphere which is beyond the radius at which this point mass is placed, that part therefore does not exert any force on the point mass. On the other hand, these shells which are present on the inside, which implies whose radii are lesser than smaller, each of them can be concentrated at the point mass in the center, isn't it? The part which are outside the radius of this point mass, they will not be exerting any force because this point mass will be inside those shells. And we've just seen because shell theorem, those will exert no force. But those point masses or those shells which have radius less than smaller, they are going to exert a force on this small m as if their point mass is the center. So what I can do is I can just consider each of those shells whose radii is less than smaller as a point mass at the center, which implies I have to basically consider the mass present within the smaller, that sphere will just take up, which is present within the smaller radius, and put them or put that total mass over there as a point mass at the center, not capital M, but the part of the sphere which is inside the radius smaller, that one.
Sir, is the answer bigger M in capital M into smaller divided by capital R cube?
Yes. So in this case, I can consider the mass of this smaller sphere of radius smaller. That mass will be concentrated at the center. If I look at the density of the original sphere, it becomes m by 4 by 3 pi r cube. That's a density. Multiply with the volume of this sphere, I get 4 by 3 pi small r cube. That is a mass which has to be concentrated right at the center of the sphere. And therefore, we get the gravitational force as g into this mass into small m divided by r square, because the distance from center is still smaller. That is the force which the point mass m experiences inside the sphere. And that will basically give us g into 4 by 3 pi cancels out, so I get gmm by capital R cube into small r. Interestingly, the force varies proportional to the distance within the solid sphere actually. Okay. Outside it will be pretty much the same as if we have taken up the entire mass as a point mass center, but for inside it varies as smaller. Okay. You can actually write down the result in a vectorical fashion as well.
Sir,
Yes.
sir, then what is the cell theory? The theorem.
Shell theorem was the previous result due to a shell.
Sir, the result is cell theorem. I mean the force.
It is force. The shell theorem says that the force exerted by a hollow sphere or spherical shell on a point mass within the shell is zero. While outside, the shell can be treated as if it was a point mass in center. That is what.
Oh,
That is the result I wrote down.
okay, sir.
You can actually write down this result in a vector manner as well. Vectorically speaking, if we consider, for example, the position vector of the point mass small m as r vector, for example, which is stretching from the center to the current location of the point mass, r vector. In this case, the vector force can be written down in this fashion, like this. The force vector is minus gmm by r cube into r vector. This minus is coming up because the direction of F is opposite this r vector. R vector goes from the center to the point mass. The force is opposite direction, and that is why it's negative. Okay. The magnitude is proportional to the distance from the center. The direction is opposite to that one, which implies toward the center actually. If you take the variation of the gravitational force due to the sphere as a function of small r, which is distance from the center, this force goes linearly, straight line, till the radius, then it just goes as 1 by r square. For outside point, it just varies if it was a point mass 1 by r square. So for inside point, it just goes, straight linearly actually. So then do something like that. Okay, I'm just posting a snapshot right now. The microphone suddenly switched. The board is hazy.
Sir,
Okay, we'll take a snapshot and send it by the way. You've done that?
yes.
Okay. Oh, your portion mathematics group by the way.
Not in mathematics, physics.
Oh, sorry, sir. Sorry, sir.
No problem. That usually happens sometimes. We'll delete from there and forward it to the other group. That's it.
I did it for the physics.
Okay. So have you already done that? Okay, fine. I mean, how will the graph for the force versus distance look like for a shell? By the because the shell, the spherical shell,
Sir,
shell.
sir,
Yes.
force versus, sir, F versus R. Sir, for, up to R it is, sir, acting as linear.
This is you see proportional to r. Rest of things are constant. Y to mx kind of thing. Yeah.
So, but if the value of small r is less than capital R,
Hmm.
s- sir, and it is gradually increasing, sir, then how come it is constant?
What is constant? I said these are constant.
Oh, okay, sir, okay, sir.
So f is like a constant into r. F is y code mx kind of thing. There's a straight line through the origin.
Okay, sir, got it.
Okay. What? How will the force between them vary? For example, if the instead of a sphere we had a shell. If I had a shell, go back to the previous thing.
So up to R it will be zero, and then it will go in the same way.
Yeah, that will be fine. For a spherical shell, the graph will be f will be zero till capital R, and abruptly they suddenly it just goes to a finite value and then goes as 1 by r square rather. That is how the force varies for the case of a spherical shell. Okay. You can see the Earth is not exactly homogeneous, but more or less the Earth's gravitation can be thought of as if we had a uniform sphere actually. So we expect that the gravitational force is going to decrease as we go inside the Earth. And if we consider, for example, the force, the gravitational force of the Earth, for example, think of a terrestrial gravitation, which implies the gravitational force of the Earth. First of all, we know that on the surface of the Earth, let's say this is the Earth itself, we are treating the Earth as if it was a uniform sphere of radius capital R, which is around 6,400 kilometers. However, the density of the Earth is definitely not constant. We know that there is a crust, and then after some time, it is a mantle. Then you have that magma present within. It's obviously quite variable density, but on average, you can think of the Earth as if it was a uniform sphere, actually. Okay. So Earth's gravitation also varies in the same manner. We can expect that the gravitation inside the Earth will vary linearly with respect to distance from the center of the Earth. In fact, if I kind of dig a tunnel, a bore kind of till some depth, let's say we just dig a boring or a well, for example, till a depth which is equal to h. H is usually not very large because I mean, so far people have not been able to dig very, very deep actually. But anyway, let us say that the boring is depth h actually. In that case, uh, you can compare the gravity at the bottom of this trench compared to that on the surface. First of all, on the surface, we know that a point mass will be pulled by the sun with a force which is equal to. Someone is coming now. Or the laptop.
So, will you explain the last concept once, the one of the solid sphere?
Are you able to see the board?
Yes, sir.
Yes, sir.
What? Yes. What if
Sir,
Sir, but
I
your
don't hear you. So voice is cracking, supposedly.
uh, my screen is showing a big A actually. The camera is connected, but the voice is not coming through. Hello? Nothing is happening.
Yes, sir.
What?
So we could see. So you can hear also.
I can't see myself.
So you switched it off now.
What?
Sir, you switched off the camera now.
No, I have switched it on.
Yes, sir. So now we can see you.
But I can't see it. My screenshot, I'm seeing a big A every time. Well, let me just log out and come back in again. I just log out and come back.
Yes, sir. It's like that only. We can't see it.
I'm just going to log out and come back in again.
Okay, sir.
Now it is fine, I believe. Yes. Okay.
Sir,
Bolo.
sir, please answer my question.
Yes, repeat your question because of my chats are gone. Yes, gravity on Earth is yes. It's not a field, but the force. It's a force actually. Force on unit mass. That's yeah. It's actually a gravitation field. Yes, that's correct. Yeah, if you just look at the on the surface, basically the acceleration due to gravity is the if we have taken a point mass m at the surface of the Earth, the radius is capital R E, which is known.
It is field.
What?
So for unit mass, it is field.
Yeah, unit mass is field. That's correct. But what I'm doing is I'm going to equate this with m into g actually. That's what happens if you just equate net force exerted by the Earth on the point mass E is nothing but the weight actually m into g. Fine. From there you can just see that small g is nothing but g into mass of the Earth by radius of the Earth whole square. That is what small g is. We can calculate the value and it will be the board is hazy. People will post some snapshot wait or Kadev. I hope so. You see G is 6.67 10 to the power minus 11. If you look at the mass of the Earth, it is around 5.96 into 10 to the power 24 kg actually. So you get 5.96 10 to the power 24 kg divided by the radius squared actually. Yeah. So divide by the radius squared. 6400 actually it's 5,900 something. Let's call it 6,400 kilometers. 6,400 kilometers implies we have meter and then square. It gives us, well, the exact radius is, let me see, 5,980 meters, I believe. Is the Earth. So approximately 6,400 kilometers. Oh, it is more. The average radius we are looking at. The equatorial radius is 6,378 kilometers, but the polar radius is 6,357 kilometers.
So what equatorial? Oh, okay.
The Earth is flattened at the poles actually, isn't it?
Okay, sir, understood.
In this case,
The
which
average.
radius will be
What?
so in this case, which radius is the equivalent?
I cannot get what is said. Can you repeat? Okay, we can take it roughly 6,400 kilometers. That gives us around. Actually, I'm taking more, so it will be useful if I take the average over there. 6,378, 6,357. Let's take 6,378 itself. So if I just do that, six, 378. Gives us 9.77. That is basically the equatorial radius. It's giving us around 9.8 meter per second square. This is 9.77 meter per second square actually. That is what the value of small g is. What if I go a bit inside? If I go a bit inside, for example, I think of a tunnel dug inside the earth. Let's say the depth is h, and we're looking at the acceleration due to gravity. Although if we just take the average, technically speaking, the earth is not actually a perfect sphere. It is in fact oblong. It's flattened at the poles over there, and I can say elongated at the radius, the equator, because of the centrifugal effects actually. So you just take the equatorial radius, will be enough. Any one hardly matters. Be slightly different. That's it. Difference 21 kilometers there, I believe. If I dig a tunnel on the Earth's surface, on the crust rather, say till a depth of h actually. This is dug till a depth of h. How much will be g, small g, at the bottom of the pit or this tunnel? What do you think about that? Not a tunnel, but a pit actually.
G into mass of Earth by radius of Earth minus h whole square.
But I can utilize the previous result. What's happening? This problem.
That one GMM by R cube into R. In case of R, it will be capital R minus H equals to M into G.
Again, the same problem.
Hello. The camera is switched off. What's happening?
I know it is automatically switch itself off. I don't know what's happening. My computer has gone a bit intelligent it seems. Automatically switching on.
Oh, nobody's able to listen. I believe. Now it is okay. Some problem is coming up. It seems it automatically. Yes, Anak, it seems it has developed a consciousness of itself. Anyway, we can use the previous error that I was saying. G capital M small m by capital R cube into small r. Instead of small r, we shall use this length, which is capital R minus h actually. So we can apply that result. It can be approached in two different ways. Either I can consider the, well, we can just use, I'm just removing small m, okay? Small m I'm just taking as 1. Which can be written out like this. So this is basically the g at the surface into 1 minus h upon re is what I get. So it decreases slightly proportional to the depth. The deeper you go, the smaller it becomes. In fact, if I was able to dig a tunnel right to the center of the Earth, at the center of the Earth, the gravitational force would have been zero actually. On the other hand, if I go up the surface, what happens then? If I just go up a bit, say I'm going to go up a bit over there to a height h, then what happens?
R equals to R plus H.
Yeah, if I just go at you can look at this because I can treat it as a point mass center in any case, by the way, which I can write down like this. This is g at the surface. If the height is not too large compared to radius, which is less compared to radius, not comparable, very small. In that case, we can actually apply the binomial approximation to write down this one as 1 minus 2h upon re. So that if I go back and put it in this previous result, then small g will now become it turns out to be this. So it again decreases. It decreases if you go down, it decreases if you go up. But the rate at which decreases faster when you go up actually. And when you go down, the rate at which decreases a bit slower, half in fact the rate. The surface is the large.
So can you please repeat?
Yeah, I was saying this is only true, however, if h is not very large compared to Re weather. I was saying that if you go up, the gravity decreases. If you go down, it again decreases. But when the rate is considered, implies that what rate with respect to height is decreasing. It is faster when we go up actually. When you go up, then the rate at which decrease becomes more actually. Okay? In fact, double that one. Okay?
Okay, sir.
Fine. Okay, today will be all for now. We just finish it today. Next time we take up the Kepler's laws basically. In fact, most of the problems in gravitation can be done with two things. One is the energy conservation, the other one is the angular momentum conservation. We apply both of them next time. Look at the screenshot is required. Okay. Somebody can post screenshot. Done it. 1 minute you said.
Sir,
So I said doing. So done.
sir, how was that rippling effect discovered?
How was? Well, theory was there for a long time after Newton's, Einstein gravitation. The theory was there for a long time, but recently it was quite recent that some kind of explosion of a supernova took place, and then the ripples were discovered. Exactly how it was obtained by measuring or just some analyzing the data actually.
Sir,
Yes,
so can you send it? Ask someone else to send it.
I
So
think
I was
Ryan has
sending it
done
from
that.
my laptop. Then the phone was not connected.
No
Straight.
problem. Ryan has done it by the way. Don't worry.
Okay, sir.
Yeah. Yes, exactly what technique they did. It is just a lot of data. Well, you see, once you go to that deep sky astronomy, then you hardly get to see things. It's more like numbers, numbers, numbers. Okay. From there, you just have to find a pattern over there. Is that okay? That is how it was discovered. The theory is for a long time. Okay.
Okay.
Yeah. General relativity was there, yes, and in fact, the idea of light bending that was observed way back in 1919 actually.
Sir, but how could those ideas or the theories come to the minds of those scientists?
How can I say? That is in mind. Einstein is gravity quantum. I do not know, and right now there is not a suitable theory of quantum gravity. There is something called huh? No, string theory is a candidate, but that is not very much suitable in many other conditions. There's now something. See, from a string it becomes a membrane. From membrane it becomes a p-brane. Nowadays, p-brane theories are there. People are looking also for theory of everything. POE. Anyway, exactly how they. I don't know about that Anak right now. I'm unable to answer the question whether gravity is quantum or not. Theories are not yet very satisfactory. Okay. But do require quantum gravity inside a black hole, for example. Isn't it? Because things are very far. In fact, they require that not only quantum gravity, also require relativistic things. We need to have a quantum relativistic gravity, actually, general gravity. Anyway, those things can be. You will get to know once things have been discovered, isn't it? If you want today, we can finish it now. I'll provide the recording later on.